Okay, for what we have in this particular part, okay, we are crossing the threshold over to vector equations. And just for some of the nomenclature we have concerning this section, okay, and still maintaining our work with matrices. Okay, if you have a matrix with only one column, this will be referred to as a column vector. And now vectors will appear with various numbers of elements. And for those that have two elements or two entries, okay, we have what are referred to as vectors in R2. And examples, you have, say, a vector U, which consists of, let's say, the entries 1 and 2. And we have a vector V, which consists of the entries -4 and 5. And if you were to write what you have as ordered pairs, now your x of 1 will be in reference to the top number, your x of 2 will be in reference to the bottom number, should you translate from matrix to ordered pair notation. And say that we have with vector u, so you have 1, 2, so your x of 1 is going to be at 1, while x of 2 is going to be at 2, so you have vector u projected out in this fashion. Now for what we have with vector v, so we have x1 is at -4, x2 is at 5, and we have this projection for v. And let's say that if you were to take the operation of addition between the vectors, so what you would be looking at would be adding together the corresponding parts. So you have 1 mapped with -4 at the top, 2 mapped with 5 at the bottom, and so we would have -3, 7. So your x01 value would be at -3, and your x2 value will be at 7. So you have this particular projection, okay, whereupon we have -3, 7. All right, and for what we have for operations with other vectors that are in R2, and we'll say that we have another couple of vectors. Okay, so we can say we have u is equal to 3, 7, and v is equal to 2, -6. And say if we have scalar multiples where we have the scalars at 5, whereupon we have 5 times u, as well as the scalar -2, where we have -2 times v. And if we're looking at those particular multiples of vectors, so you have 5u, so you have 5 projected over 3 and 7, so we come out to 15 and 35. So you have 5 times 3 at the top, 5 times 7 at the bottom. And for -2 times v, okay, so you have -2 times, okay, you have 2, -6, so you have projecting, you have -2 times 2 is -4, -2 times -6 is +12. And if I were to add together, okay, the vectors 5u and -2v, so we already have 5u and -2v stored, and adding together, and we have for the outcome for the sum of these vectors, we have the overall projected vector at 1147. Now, for what we have in the case of vectors in Rn, if n is a positive integer, then vectors in Rn can be written in n by 1 column matrices, such as where we have v is equal to v of 1, v of 2, v of 3, 4, 5, and you have ellipses, and where the last element would be at v of n. And if you have it such that all the entries are 0, okay, you will have what will be regarded as a 0 vector. And so again, we have a 0 vector is a vector whose entries are all 0 and will be denoted by 0. Now, in the case of algebraic properties of vectors, and say if you have vectors uv and w in Rn, and you had the scalars c and d, we have the various properties. So you have the commutative property of addition, so you have u plus v is equal to v plus u, and we have with the vectors u, v, and w involved, okay, we have the associative property of addition. You have the quantity of u plus v followed by the sum of w, and if we rearrange the parentheses going from surrounding the first two to the last two vectors, we had this equal to u plus the quantity of v plus w. For the additive identity, okay, if you have u plus 0, that is 0 plus u, which will come out to u. For the additive inverse property, okay, you're looking at additive inverses that will add up to 0. And for the distributive properties, Okay, so you have the scalar c times the quantity of u plus v. So you have c times u plus c times v. And likewise, if I had the sum of scalars multiplying a vector, okay, you have c times u plus d times u. And then we have in the realm of multiplication, we have with the associative property of multiplication, we have c times the quantity of d times u. And if I shift from the last two vectors multiplying to the first two, I have the quantity of c times d, and then we have u on the outside. Okay, so we have for the multiplicative identity, I have 1 times u is equal to u. Now, in looking at what we have, what will be in the crossover to what will be referred to as linear combinations, and we will re-enter the use of matrices and echelon form and all that good stuff. For linear combinations, if you're given vectors, okay, so you have subscripted with 1, 2, 3, all the way out to n in Rn, and you have scalars, okay, such as C1, C2, C3, Cn, where you have the subscripted values to match throughout. Then you're going to have the vector y defined by where we have y is equal to the summation of the product of c times I, c of I times v times I as I goes from 1 to n. And so we would have c1 times v1 plus c2 times v2 plus c3 v3 all the way out to c of n, v of n. And y is going to be referred to as a linear combination of these vectors with the weights from the scalars, where we have it c1, c2 all the way up to cn. And you can have different letters, okay, for the vectors and the scalars. And for instance, okay, you can have a set of v, you could have a as a letter, and okay, and say that we have so you have three vectors, okay, and we have so we have a of 1, a of 2, and we have b, and it says here to determine whether our vector b, okay, kind of like serving the same purpose as what we have with y, but we had the letter b instead. It says to determine whether b can be generated as a linear combination of a of 1 and a of 2. In other words, it's asking can we have the weights x of 1 and x of 2 applied such that x of 1 times a of 1 plus x of 2 times a of 2 is equal to b. And looking at what we have here, so in testing out, say like before I had c1 v1 plus c2 v2 yada 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 is equal to y. Well, I'm just same purpose, same premise, just different letters, but same concept. And so we have applying the vectors for a of 1, a of 2, as well as b explicitly. This is what we have in the setup. And now combining our elements, in case you have top row, you have x1 plus x2, 2x of 1 plus 4x of 2, 3x of 1 plus 7x of 2, and we have equal to, again, b, where we have from top to bottom, we have 2, 4, 14, and setting up what we have, taking the top row all the way down to the bottom row, we have this combination of equations in the system. And if we set this up where we can apply and transition over to reduced row echelon form. Okay, so I have in matrix form, so I have 1, 1, 2, 2, 4, 12, 3, 7, 22. And again, the leading entry from the top row, I have 1. And to put this in echelon form, I'm going to make, again, the 2 and the 3 as zeros. So we have R2 minus 2R1. And then I have third row minus 3 times the first row. So I have this transition. And if I shift on over, okay, we have in the second row. Okay, so the non-zero element is going to be 2. And so if I want to change this over to a 1, since I'm going to be looking at the reduced echelon form, so I can take half of 2 and thus half of the second row. So I have 0, 1, and 4. And if I make this 1 as the only non-zero value in the second column, so I'm going to change this one at the top and the 4 at the bottom, both of them to 0. So I'm going to follow through with R1 minus R2, as well as R3 minus 4 times R1. So I come out to 1, 0, negative 2, 0, 1, 4, and we have 0, 0, and 0, and we have 0 is equal to 0. And for the top, I have x of 1 is equal to -2, and x of 2 is equal to 4. And we have that b is indeed a linear combination of a of 1 and a of 2. Now, just some of the added terminologies. Now, we have what is referred to as span, and this is just a notation for what we have indicating linear combination. So you have the span from v of 1 to v of n, so you have your linear combination from c of 1, v of 1, adding all the way up to the combination c of n, v of n. And if I have the span of just a letter v, this would be the scalar multiple c multiplying v. For the span of u and v, we can take the scalars c and d, where we can just say c times u plus d times v. And for the span of a of 1, a of 2, we can say we have with x1 and x of 2 as scalars, we can say we have x of 1, a of 1 plus x of 2 times a of 2. And just to sort of test out once again, a little history repeating, but with a different set for a of 1, a of 2, and b. Okay, and it's asking here if span of a1, a2 is a plane through the origin in R3, is B in that plane? In other words, is B going to be a linear combination, or can be expressed as a linear combination of a of 1 and a of 2? So we have this bit of history to repeat, and so again we have combining, okay, and just a little shorthand. Okay, so we don't have to put in the variables, just go ahead and cut to the chase. All right, so you have 1, 2, 3, 2, 6, 8, 3, 7, 1 from the top, middle, and bottom rows of A1, A2, and B. And again, getting this to reduced echelon form. So I can convert the 2 and the 3 to zeros. So again, take away twice R1 from R2 and 3 times R1 away from R3. So I had this set up, and to make the 2 in the middle, okay, as 1, I can take half of the second row and leaving the top and bottom rows unchanged. Okay, I have this, so I got 1, 0, 0, and then we had the pivot position next, okay, with the one that is in the middle, and I can make the 2 above and the 1 below as zeros. So I can take R1 minus 2 times R2, as well as R3 minus R2. So I have 1, 0, 1, again 0, 1, 1, and 0, 0, negative 9. Now I have a stumbling block because the bottom row says that 0 is equal to negative 9, and that is false. So there is no solution, and so we have in effect that B is not in the same plane as A of 1 and A of 2. So B is not in the span of A of 1 and A of 2.